There's a fundamental problem with language when we try to describe the universe. We use words to capture cosmic phenomena, but the universe doesn't speak English, it speaks mathematics. And sometimes when we attempt to translate mathematical truths into human language, we create names so poetic, so captivating, yet so fundamentally misleading that they set our understanding back by decades. The worst offender in the history of physics is the term black hole. When you hear those words, what do you visualize? You see a hole, a cosmic drain, a dark, empty void where matter goes to die. You imagine a place of absolute darkness, lurking in the shadows of the galaxy, invisible and silent. But Stephen Hawking's revolutionary work revealed that if you actually traveled there, if you positioned a spacecraft millions of miles from a supermassive singularity, you wouldn't witness blackness at all. You would see the brightest, most violent, most spectacular engine of light in the entire cosmos. You would witness a ring of fire so intense that it makes our sun appear like a dying ember. And even if you stripped away all the surrounding gas and dust, even if you observed a completely isolated black hole in perfect vacuum, Hawking's physics tells us it still wouldn't be black. It glows, it has temperature, and if you wait long enough, it explodes. What if I told you that Stephen Hawking's most famous discovery proves that black holes are actually the universe's most efficient recycling machines, slowly converting their entire mass into energy over cosmic timescales? That these objects we consider eternal prisons are actually temporary furnaces that will eventually detonate with the force of billions of nuclear weapons? This is the story of how Stephen Hawking revolutionized our understanding of black holes, proving that they're neither black nor holes, but rather cosmic engines that challenge everything we thought we knew about the nature of reality itself. Before we explore Stephen Hawking's groundbreaking discovery of black hole radiation and why it proves these cosmic giants will eventually explode, make sure to hit that subscribe button, because we're about to uncover the physics that transforms our understanding of the universe's most mysterious objects. Stephen Hawking's journey into black hole physics began with a simple but profound question that would revolutionize our understanding of these cosmic objects. What happens to the entropy of a black hole? This wasn't just academic curiosity, it was a fundamental challenge to the laws of physics as we understood them. Nature loves entropy, disorder. The second law of thermodynamics tells us that entropy always increases in any closed system. But black holes seem to violate this sacred principle. When you throw a messy, disordered encyclopedia into a black hole, it disappears completely. The disorder seems to vanish from the universe entirely, which should be impossible according to fundamental physics. Hawking realized that this apparent violation of thermodynamics pointed to something deeper. Either our understanding of black holes was incomplete, or our understanding of entropy itself needed revision. The physicists decided to tackle this problem by combining two of the most successful theories in physics. Einstein's general relativity, which describes gravity and the geometry of spacetime, and quantum field theory, which describes the behavior of particles and fields. What Hawking discovered when he merged these theories shocked the physics community and changed our understanding of black holes forever. He found that black holes aren't the simple, static objects that classical physics suggested. They're dynamic, evolving entities that interact with the quantum fabric of spacetime in ways that nobody had previously imagined. The key to Hawking's breakthrough was his realization that space itself is never truly empty. Even in what we call vacuum, space is a bubbling foam of virtual particles, particle and antiparticle pairs that constantly pop into existence, borrow energy from the vacuum, and then annihilate each other in fractions of a second. This quantum activity happens everywhere all the time, but it's usually unobservable because the particles cancel out so quickly. But Hawking asked a crucial question. What happens when this quantum activity occurs right at the edge of a black hole at the event horizon? This is where the physics becomes truly extraordinary and counterintuitive. Think about the implications of what happens at the event horizon. We're not talking about some distant theoretical boundary. We're discussing the most extreme environment in the known universe, where spacetime itself is stretched to its breaking point, and where the normal rules of physics begin to break down. Hawking's calculations revealed that when virtual particle pairs appear near the event horizon, something remarkable occurs. Imagine two particles materializing right at the boundary of the black hole. One particle appears just inside the event horizon, while its partner appears just outside. The particle inside gets trapped by the black hole's gravity and falls in, while the particle outside escapes into space as real, observable radiation. This process, which we now call Hawking radiation, means that black holes are constantly emitting particles and energy into the universe. But here's where the physics becomes truly mind-bending. The energy for these escaping particles has to come from somewhere, and that somewhere is the black hole itself. Einstein taught us that energy and mass are equivalent, E mc2. So when a black hole loses energy through Hawking radiation, it also loses mass. The particle that falls into the black hole actually carries negative energy, effectively subtracting mass from the black hole's total. This means that black holes are slowly, agonizingly evaporating, bleeding their mass away into the universe as thermal radiation. The implications of this discovery are staggering. Black holes aren't eternal prisons. They're temporary objects with finite lifespans. They have temperature, they emit radiation, and they're slowly shrinking. In thermodynamic terms, they're alive, constantly exchanging energy with their environment. For massive black holes, this evaporation process is incredibly slow. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely. The temperature of such a black hole would be billionths of a degree above absolute zero, far too cold to detect with current technology, but theoretically present nonetheless. But here's where Hawking's physics reveals something truly spectacular. As black holes shrink, they get hotter. The smaller a black hole becomes, the more intense its Hawking radiation becomes. This creates a runaway process that accelerates as the black hole approaches the end of its life. Let me ask you something that might fundamentally change how you think about cosmic evolution. If every black hole in the universe is slowly evaporating and will eventually explode, what does that mean for the ultimate fate of the cosmos? Share your thoughts in the comments below, because this question touches on some of the deepest mysteries in physics. Hawking's mathematics revealed the complete life cycle of black hole evaporation, and it's far more dramatic than anyone had imagined. As a black hole loses mass through radiation, its event horizon shrinks, its surface gravity increases, and its temperature rises. What begins as an imperceptibly slow process gradually accelerates into one of the most violent events imaginable. The physicists calculated that in the final stages of evaporation, when a black hole has shrunk to the size of a proton, it doesn't simply fade away quietly. Instead, it releases all of its remaining mass energy in a single, catastrophic explosion. We're talking about the energy equivalent of millions of hydrogen bombs detonating simultaneously in a space smaller than an atomic nucleus. This final explosion represents the complete conversion of the black hole's remaining mass into pure energy, the ultimate expression of Einstein's mass-energy equivalence. The object we think of as an eternal prison, the cosmic phenomenon we imagine as a silent grave, ends its existence as one of the most powerful explosions possible in the universe. But Hawking's discovery raised even more profound questions about the nature of reality itself. If black holes evaporate completely, what happens to all the information that fell into them over their lifetimes? This question, known as the black hole information paradox, strikes at the heart of quantum mechanics and our understanding of how information behaves in the universe. Quantum mechanics tells us that information cannot be destroyed. It can be scrambled, transformed, or hidden, but never completely eliminated. If you burn a book, the information isn't lost. It's converted into the pattern of ash, smoke, and radiated heat. In principle, if you could capture every particle and photon, you could reconstruct the original book by running the physics backward. But if a black hole evaporates into random Hawking radiation, where does the information go? Does the universe actually delete files? This paradox has puzzled physicists for decades and has led to some of the most exotic theories in modern physics. Hawking himself initially believed that information was indeed destroyed in black holes, but later research has suggested more exotic possibilities. The leading theory today is called the holographic principle, and it's so strange that it challenges our basic understanding of reality. The holographic principle suggests that when information falls into a black hole, it doesn't actually go inside. Instead, it gets encoded on the surface of the event horizon, like a holographic image that contains all the information about a three-dimensional object in a two-dimensional surface. When Hawking radiation is emitted, it carries this encoded information back out into the universe. This leads to an even more mind-bending possibility. If black holes are essentially holograms, and if black holes are just extreme manifestations of gravity and space-time curvature, then perhaps our entire universe is holographic. Maybe everything we perceive as three-dimensional reality is actually a projection from information encoded on a two-dimensional surface at the edge of the cosmos. Hawking's work on black hole radiation has also revealed the deep connections between gravity, thermodynamics, and information theory. Black holes obey the laws of thermodynamics just like any other physical system. They have temperature, entropy, and they exchange energy with their environment. This suggests that gravity itself might be an emergent phenomenon arising from more fundamental information processing principles. Recent developments in black hole physics have only deepened the mysteries that Hawking's work revealed. Advanced computer simulations of black hole mergers have confirmed many of his predictions about how these objects behave, while also revealing new complexities in their evolution and interaction with space-time. The detection of gravitational waves from merging black holes has provided direct observational evidence for the dynamic nature of these objects. We can now observe black holes in the process of formation, collision, and evolution, confirming that they're far from the static, unchanging objects that early physics suggested. Modern observations have also revealed the incredible diversity of black holes in the universe. From stellar mass black holes formed by collapsing stars to supermassive black holes containing billions of solar masses, these objects span an enormous range of sizes and properties. Hawking's radiation theory applies to all of them, though the timescales for evaporation vary dramatically. The physicist's work has also influenced our understanding of the early universe and cosmic evolution. In the first moments after the Big Bang, conditions were so extreme that microscopic black holes might have formed and immediately evaporated through Hawking radiation. These primordial black holes could have played a crucial role in the universe's early development and might even account for some of the dark matter we observe today. Hawking's discovery that black holes have temperature and entropy has also led to new insights about the fundamental nature of space-time itself. If black holes can have thermodynamic properties, it suggests that space-time might be made up of discrete, quantized units, a kind of cosmic pixels that give rise to the smooth geometry we observe at large scales. The implications extend far beyond black holes themselves. Hawking's work suggests that the vacuum of space is far more active and complex than we previously imagined. The quantum fluctuations that give rise to Hawking radiation are happening everywhere, all the time, though they're usually too subtle to observe directly. This quantum activity in the vacuum might be responsible for the accelerating expansion of the universe that we attribute to dark energy. The same quantum processes that cause black holes to evaporate might be driving the cosmos apart at ever-increasing rates. Hawking's radiation theory has also opened new avenues for understanding the relationship between quantum mechanics and gravity. The fact that black holes emit thermal radiation suggests that gravity and quantum mechanics are more deeply connected than Einstein ever imagined. This connection might hold the key to developing a unified theory of quantum gravity. The physicist's work has practical implications as well. Understanding Hawking radiation is crucial for any future technology that might involve creating or manipulating black holes. While such technology is far beyond our current capabilities, the principles Hawking discovered will be essential for any civilization that achieves such advanced capabilities. Recent theoretical work has also suggested that Hawking radiation might be detectable in laboratory settings using analog systems that mimic black hole physics. These analog black holes, created using sound waves, light, or condensed matter systems, might allow us to study Hawking radiation directly for the first time. The search for primordial black holes, tiny black holes that might have formed in the early universe, continues to be an active area of research. If such objects exist and are currently evaporating through Hawking radiation, they might be detectable as gamma-ray bursts or other high-energy phenomena. Hawking's work has also influenced our thinking about the ultimate fate of the universe. If all black holes eventually evaporate, and if the universe continues expanding and cooling, we might be heading toward a future where all matter has been processed through black holes and converted into radiation. This heat death scenario represents the ultimate triumph of entropy over order, but even this bleak future contains elements of hope and wonder. The radiation emitted by evaporating black holes carries information about everything that ever fell into them. In a sense, black holes might be the universe's ultimate recycling system, ensuring that no information is ever truly lost, just transformed and redistributed. The physicists' discovery that black holes explode also raises intriguing possibilities for the far future. As the universe ages and cools, evaporating black holes might become the primary source of energy for any civilizations that survive into the deep future. The final explosions of black holes might provide brief moments of intense energy in an otherwise cold and dark cosmos. Hawking's work on black hole radiation represents one of the most profound discoveries in the history of physics. It revealed that objects we thought were simple and static are actually complex, dynamic systems that challenge our understanding of space, time, information, and reality itself. The physicist showed us that black holes aren't holes at all. They're cosmic furnaces that slowly convert matter into energy over vast timescales. They're not black. They glow with thermal radiation that encodes information about everything they've consumed. And they're not eternal. They're temporary structures that will eventually explode with tremendous violence. Perhaps most importantly, Hawking's work revealed the deep unity underlying seemingly disparate areas of physics. His discovery that black holes have temperature and entropy showed that thermodynamics, quantum mechanics, and gravity are all aspects of a deeper, more fundamental reality that we're still working to understand. The next time you hear someone refer to a black hole, remember Stephen Hawking's revolutionary insight. These objects aren't dark voids where things go to disappear. They're blazing engines of physics that reveal the deepest secrets of the universe. They're cosmic teachers that challenge our assumptions and force us to expand our understanding of what's possible. Hawking's radiation proves that even the most extreme objects in the universe obey the fundamental laws of physics, but they do so in ways that stretch our imagination and challenge our preconceptions. Black holes aren't the end of physics. They're laboratories where the most exotic phenomena in the universe play out according to principles we're still discovering. So the next time you look up at the night sky, remember that scattered throughout the cosmos are these incredible objects. Not holes, not voids, but cosmic engines slowly converting their mass into energy, glowing with invisible radiation, and destined to end their lives in spectacular explosions that will illuminate the universe long after the last stars have died. If this exploration of Stephen Hawking's revolutionary discovery of black hole radiation has opened your eyes to the true nature of these cosmic phenomena, make sure to smash that like button to support more deep dives into the physics that shapes our universe. Subscribe to our channel and hit that notification bell so you never miss our latest investigations into the fundamental forces that govern reality. Share this video with anyone who's ever wondered about the true nature of black holes, because understanding Hawking radiation might be crucial for grasping the deepest mysteries of space, time, and information. And let me know in the comments. If black holes eventually explode and release all their information back into the universe, what does that tell us about the nature of reality itself? How does Hawking's discovery change your understanding of cosmic evolution and the ultimate fate of the universe? What other seemingly permanent features of the cosmos might actually be temporary phenomena that we don't yet understand? Drop your thoughts below and join our community as we explore the revolutionary physics that continues to transform our understanding of the universe. The cosmos is far stranger and more dynamic than we ever imagined, and Stephen Hawking's work on black hole radiation is just the beginning of discoveries that will reshape our understanding of reality itself.